All right, so today we have quite a bit to do. I ran a little bit behind last time, so I have some catching up to do today. Um, and let me give you the schedule. So today um, I'm going to complete, I did start chapter 4 last time, that example from chapter 3. And I'll be completing chapter 4 today and actually showing you a couple more things from section 3 of chapter 3 also today. I'll do that first. Next Monday, we're going to be covering what's called linear regression. So we're going to look at scatter plots, which is section 3.4, and then we'll look at a couple sections in chapter 5. Typically, it's a very easy topic. I can cover it all in one day, even though that type of topic tends to be, when developed fully, can be a complete course or even a year course. But in this course, it's just a very gentle introduction to regression. Very easy. It's even taught, what I'm teaching is even taught in high school in Algebra 2. So it's very, very simple. You won't have any issues with it. And then next Wednesday, I will have another quiz, I believe. Let me think about that for a minute. I think so. I think I'll let you know for sure on Monday, but I think next Wednesday will be quiz number 2. I'll give you more details of that on next Monday. And also, there will be a review for the first test, okay, which will be the following Monday, and I believe that's March the 1st. All right, so that's the tentative plan. So I'm going to get going, and I see somebody has sent me something in the chat. All right, somebody is driving, that's okay. So if you're listening, that's okay. I know you can't turn your video on when you shouldn't be watching me anyway while you're driving, so that's fine. All right, so let's get started. Now, also, I should tell you that as far as homework, I will be assigning some homework. I'm not going to be able to get to it until tomorrow in the afternoon, later in the afternoon, in terms of posting some homework. But there will be homework for both chapters 3 and 4. I might even create 2 assignments, 2 homework assignments. And it'll be due the next week. Maybe chapter 3 might be due on Sunday. I'll have to think about it, or Monday. And then the other one will be due on Wednesday before we have our review for our first test. All right, but I'll give you more details about that. I'll send you an email about the homework, but don't expect anything until tomorrow afternoon. All right, so let's share the screen and let's go to chapter 3, just to finish up chapter 3 quickly. All right, now in chapter 3, this is section 3, we went over last time how to construct a histogram. And this is just, I might have shown this to you last time, but just reviewing. The things that you can look at with a histogram are things like, where is approximately the center of the data distribution? How variable or how spread apart are all the data points? The general shape, whether it's symmetric or skewed. I talked about skewness last time. Whether how many peaks there are. It could be 1 peak, could be 2 peaks. We'll talk about that. We could talk about that in terms of interpretation, and also any outliers. And I'm going to talk about outliers today, how to figure them out. So those are the types of things that you can observe when you're looking at a histogram. And much of it is just common sense when you look at it. Okay. So let's get to, I'm going to get to a further slide here. Now, one thing about—
Excuse me, Professor, I'm sorry, I just got in. For some reason, I was having difficulty logging in. I just wanted to make sure you marked I was here.
I don't do marking. I get a report from Zoom.
Okay.
So it just shows up when you arrived and the amount of minutes that you're online. All right.
Okay.
So that's how I determine if you're here and you've been here a significant amount of time.
Okay. Just wanted to make sure.
All right. Now in section 3.3, I just want to mention to you, I've looked over this part right here. If you've been reading, it says class intervals of unequal widths. We'll skip that. All right. So that part we will not cover. So this section here, slide 32 up to I think 38. I'm not going to cover any of that. So yeah, I think it's enough just to know how to do histograms with equal widths. Unequal widths, it's a more advanced topic and it's unnecessary for this course. So we're going to skip those slides. The shapes, we talked about this last time, histogram shapes. We could talk about the peaks of the histogram. It could have one peak, which we would call unimodal. It could have two peaks, bimodal, or it could have more than two peaks. It could be multimodal. The word mode, M-O-D-E, is a measure of the center of a distribution, of a data set. And it's basically the most frequent number in your data set. All right, the number that's in your data set that is repeated the most frequently. All right, so they just made some drawings here. A is looks like what's called a bell-shaped curve or normal curve. We're going to talk about that today a little bit towards the end of the session. Here's bimodal, and then multimodal. Looks like somebody's face if you look at it sideways, but and then you can also look at how spread out the data is. Now these are all symmetric, by the way, right? They're all symmetric. So symmetric basically means if you draw a vertical line through the middle of the left side and the right side of the vertical line would be mirror images of each other. And these are three examples of symmetric shapes. The one in the middle is the one that we're going to pay more attention to, and also the one on the right too. Those are the more bell-shaped or normal curves. And then we talk about skewness. So if something is not symmetric, it's skewed. It's skewed either to the left or to the right. And this is important. And I'm telling you, it's very important topic here, skewness. So you have to know that these definitions. And of course, if it's open book, you can always look things up, but it's better to know it and not have to look something up. Skewness means most of the data points is either to the left or to the right. A positively skewed data set means most of the data is to the left and it's tailing to the right. So let me say that again. Positively skewed, and another term for it is right skewed, means much of the data is on the left and it's tailing off to the right. So the skewness has to do with where it's tailing off. So fewer data points where it's tailing off to the right, it's called right skewed. And if it's tailing off to the left, it's called left skewed or negatively skewed, where most of the data is on the right. Okay, and so this is what they look like. Let's get to the next slide here. On the left at part A, that's the right skewed or positively skewed. And on that's the A there. So diagram A is positive skewness, or all right, positive skewness to the right. And negative skewness is that's B there, where it's tailing off to the left. So that's called also left skewed. Please don't get these mixed up. On the final exam, they typically have a question about this. I see so many students get them backwards and they get 0 points. You get 0. Could be a 10-point question. It's easy and you get 0 for it. And it could be the difference between a B and a C in your grade, overall grade. It's really important that you understand. And I point out things that you make sure that you know this, because it's a very easy thing to know. But if you don't know it, you're probably going to get it backwards. You're going to get it wrong. And these are, of course, the normal, what we call a normal curve, bell-shaped curve. They're symmetric, and also they tail off both to the left and to the right. Okay. Now they make a distinction here between normal, they call heavy tail, light tail. We don't get into much in terms of the the tails in terms of whether they're heavy or light-tailed in this course. That's more of an advanced topic, but just know bell shape is typically the normal curve, and that's what we're going to pay attention to this course. All right, so this slide here that makes that distinction, I'm not going to make a big deal about that here because it's more important for more advanced courses. All right, and then I think the last slide I want you to look at is this actually slide 69 here. Now, when we were last time when we were talking about frequency distribution tables and their corresponding histograms, the histogram was just rectangles for different classes, and the height of the rectangle was either the frequency or count or a relative frequency. But I also showed you last time what was called cumulative frequency, sort of a running total. We could have a cumulative frequency or a cumulative relative frequency. And if we were going to plot it, it would look something like this. All right, it would be sort of a bunch of line segments, and each dot represents cumulative frequency. So, for example, this particular chart here along the x-axis is, I believe, amount of rainfall. I don't know. I guess that might be in inches or feet. I'm not sure the measurement, but regardless, the height of the dot is the cumulative relative frequency. So, for example, between 4 and 5, from 4 up to 5 inches, the frequency is the height, or the cumulative frequency, the height of this dot at number 5. At number 6, it would be the cumulative frequency when the rainfall is from 5 to 6 inches, up to 6 inches, and so forth. So eventually you would get all the way up to cumulative relative frequency of 1, because that's the total relative frequency. So the very last one here, between 13 and 14, would have a cumulative relative frequency of 1, which means all the data points are less than 14. All right. So you've probably seen this before. If you ever take the SATs, you took the SATs, they typically have questions like this, these types of charts on the SATs. Are they useful? Yes, in some fields, people use this. The histogram is more useful in people who do statistical research. People tend to use that more often than they use this chart. But this is something that you can see in whatever field that you are in. You can see one of these charts. All right. So if I wanted to know, for example, what percentage of the data is less than, I guess this looks like it's around 10. Okay, around 10. So what percentage of the rainfall in the data set is less than or equal to or less than 10 inches? The answer would be 60%. All right, you just go up, draw a vertical line up to from 10 all the way up to your dot, and then run your finger across, and you see it's 0.6. 0.6 is 60%. All right, so that's how you read one of these charts. Any questions about that? All right. So that's it for this, for chapter 3. I wanted to finish that up. And if you hear a dog in the background, that's dog sitting today because no one else is in my house. So hopefully that won't be too distracting. He's tends to park a lot. All right. So let's get to the next one. And let's see if I can find that one here. Just give me a second here. I think this is it here. No, that's not it. So let me go back. Sorry about that. Pick the wrong one. And let's see if I can find it. This is it. All right. Sorry about that. All these PowerPoints look the same when they're really small writing. All right, so this one is chapter 4. Chapter 4 has to do with descriptive statistics that are not that are mostly not graphs, but I will introduce you to a graph today that is very important that you can add to the graphs that you've learned. But anyway, this is the section where we talk about the mean and the median, and we mentioned that last time. And let's just go to this slide here. When I introduced the mean to you last time, the sample mean, we use the Roman letter X with a bar above it. Small x with a bar above it means sample mean. All right. So if we collect a sample, a subset of the population, then the sample mean is the sum of all the values in the data set divided by the number of values in the data set, or number of observations in the data set. So if there are n, if the sample size is n, we're just saying n. It could be 20, it could be 100, it could be 1,000. And we add up all the x's, which means all the values in your data set, and divide by the number of values, we get our mean. And the sum, I showed this to you last time. The sum symbol is this Greek symbol sigma. It's a large, it's a capital sigma. It's a sigma x in the numerator divided by n. That means sum up all the x's and divide by the sample size, the number of values in your data set. It's very easy. I think you've all done averages before, and that's how you calculate it. All right, and that's this is for a sample mean. All right, so that is the sample mean, and there are examples in the slides and there are examples in the books, but I think this is pretty, for most of you, probably all of you, this is probably very simple to do. And you don't even need to actually do this, because I told you you can enter the data as a list into your calculator and go to one variable statistics and just look it up. How easy can that be, right? So you don't even need to add them all up. But in case your calculator breaks down and you needed to do this on the fly, this is how you would do it. And I guess all of you have done averages before. All right. Now, again, when we look at samples and we calculate different what we call sample statistics, we use the term statistics for samples, such as the mean, and we'll talk about the standard deviation in a little bit. We use our English or Roman letters, okay? In this case, X bar for the sample mean. Now, if we happen to have a population and we wanted to calculate the population mean, we're going to use a Greek letter. So Greek letters are going to be used for population, what we call parameters. So the word parameter refers to population summaries, and statistics refers to sample summaries. So for the population mean, it's a population parameter, and we use the Greek letter mu. All right, looks like a U, but it has sort of like a line that extends below the curve of this letter, and that's called mu. All right, MU, that's how you pronounce it, and it's the population average. Now, as far as your calculator is concerned, the formula is exactly the same. We add up all the values in the data set and divide by the number of values. It's just we have to know whether we have a sample or population mean, but the formula is basically the same. There's no difference. So the calculator decided, Texas Instruments decided to use X bar in one variable statistics for the mean. But just know if we were calculating the population mean, we would look it up in the same place. It's just the same number. Again, your calculator doesn't know whether what you've entered into a list is a sample or a population. It doesn't know. It doesn't need to know. So same formula, it doesn't really matter. It's just I wanted to introduce you to the Greek letter mu for population mean. Okay. All right. The median, of course, is the next thing that we talked about. All right. Now, median is if we order, and my dog is yapping at me, but we'll have to ignore it. If we took a data set and we sorted the data set from smallest to largest, the median is the number in the middle. Now, if n, which is the sample size or the number of values in your data set, is an odd number, like 15 or 25, something like that, then it's literally the median is the number in the middle. If the number of values in your data set or the sample size is an even number, like 16 or 26, then you take the average of the two middle values, and that gives you the median. But again, you don't have to worry about it, because if you, again, enter a data set directly into your calculator and you don't have to order it, your calculator can figure out the median for you. And again, one variable statistics gives you that median, right? Sample median, the population median, doesn't matter. It's the same thing. It's the value in the middle in an ordered data set. Okay? There's no special symbols for the median. So people just say median, all right? They just write out the word median. All right, and that's pretty much what it is. It's the number in the middle. All right. So that's the median. And again, since we don't have to calculate it, we can actually just look it up. Not much to discuss about the median. Now, we talked about this last time, comparing the mean and median. As I mentioned last time, this is a very important topic for both the first test and the final exam. They do test on this frequently in the final exam. And what is the final exam? Basically, they'll give you shapes, like, whether they're symmetric or left skewed or right skewed, and they're going to ask you whether the mean, what's the relationship between the mean and the median. So again, this is a slide right here. This is a slide number 19 in the section 4.1. Shows you exactly what you need to answer that question. All right, and you have to answer it beautifully. What do I mean by beautifully? I mean completely. You can't just say the mean is greater than the median, and let's leave it at that. That's, you get 0 points for that on your final exam. You have to explain the following. If you have a right skewed or positively skewed distribution, and which one of these three is it? Can anybody tell me? Positively skewed or right skewed? Is it the one on the left, the middle one, or the one on the right? Which one is positively skewed?
The middle.
The middle. That's exactly right. And the reasoning behind it is that the mean is affected by outliers. In other words, with a right skewed distribution, we have unusually large numbers. Not many of them, but some. There's some unusually large ones. And what they do, what those large numbers do, is that when we add those large numbers into and add them up with all the other numbers in the data set, it makes the mean get larger. All right. So the mean typically is larger than the median when we have a right skewed, another way of saying it, positively skewed distribution, the one in the middle. Now, why isn't the median affected? Because the median is the number in the middle. The number in the middle will not be affected by either large or small values, So the median stays the same. So here's what you need to say when you write it out on the final exam. You say something like, you look at it and it is right skewed. You say the mean is going to be larger than the median because the mean is increasing because of the large outliers, and the median is unaffected by them. And that's why the mean is bigger than the median. The one on the right is what's called left skewed or negatively skewed. It's where it's tailing off to the left. In this case, we have a few very small values. That's why it's tailing off to the left. And what those small values are doing, when you add them in with all the other values, when you calculate the mean, is that makes the mean go smaller. All right, so the mean gets smaller because of the unusually small values in your data set. But again, the median is unaffected by these unusual values. So the median stays the same, but the mean gets smaller. And that's why the mean is typically less than the median for a left or negatively skewed distribution. Now, the one in the middle, if it's perfect, if it looks perfectly symmetric, then the mean would be equal to the median. But of course, most data is not perfect. But if it's approximately symmetric, we would expect the mean to be approximately the same as the median. Okay. Any questions about that? Very important slide here. Make a note of it. If you're taking notes, please make sure that you remember this particular topic here for your final exam. Again, like I said before, it would be a shame to get this wrong because it's such an easy few points on your final. I mean, it's really an easy topic compared to everything else you're learning. So please don't get this wrong on your final. All right. And let's see. And then we have one more thing that we're going to talk about a little bit later. This will come up later in the course, on the third part of the course more. And it's the idea with categorical data that sometimes, because we're counting in categorical data, typically we're counting things like the number of cars in the car lot or whatever we're counting. Because we're counting, we can come up with what are called proportions. Right? So categorical data, typically we are counting frequencies and relative frequencies. And that's where we come up with bar charts and things like that. And we use this type of symbol here to represent if we have a sample. And suppose the sample is basically, we're asking people a yes/no question on a questionnaire. All right, it's a yes/no question. So some people are going to say yes, some people are going to say no. Suppose we're interested in the yeses, and we call that a success. So when we see somebody answer yes, that's a success. All right. So if we wanted to calculate the proportion of successes in the data set, so if there's, let's say, 100 people that we've asked that question to, and let's say 30 of them said yes and 70 of them said no, then the number of successes would be 30 in the numerator, and your denominator would be the number of people we asked the question to, which would be 100. 30 divided by 100 is 0.3. Your sample proportion of successes is 0.3. So we use the symbol P with a little hat above it to represent the sample proportion of successes. All right. We're going to talk more about that later in the course. But I'm introducing you to this symbol now. And typically, if we were looking at a population, we would use the letter P by itself to represent the population proportion of successes. All right. And that's basically something that we're just showing you up front for now. And they give you an example here. All right. 15 cell phone users asked if they're satisfied with their cell phone service. So they answer they're satisfied, that's an S. If they answer they're not satisfied, it's an F. And here are the responses for the 15 people. And we want to know what's the proportion of them that answered S or satisfied. Well, you just count the number of S's. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of the 15 answered yes. Right? All right, makes sense? And that's 60%. So that's 0.6 is our sample proportion of people who said they're satisfied. All right, and it's that simple. All right, and that's it. Well, again, we'll talk about that at a later date. Any questions about proportions? That's 4.1. So let's leave that and we'll go to 4.2. Let's see if I can find it here. 4.2, I get this one here. I hope this is the right one. There it goes. Now, besides the mean and the median that were mentioned, of course, we didn't see anything about the mode, but I might have missed it. It's in your book about the mode. The mode, again, is the most frequent number in your data set. By the way, if your data set doesn't have, if all the numbers in your data set are only listed once, then there's no mode. There's just one value for each. There's only one repetition for each number in the data set, so no mode. Another important topic is variability. This is actually a critical topic in statistics because that, when we ask people questions or we measure things, we're typically going to get some variable answers. There's going to be some natural variability in the data. The question is, how do we measure variability? Well, one of the measurements is called the range. It's the simplest one. And I might have mentioned to you about this earlier at an earlier meeting where we were calculating for a frequency distribution table, we were calculating the width for each of the classes. And I told you to take the largest value, subtract the smallest value, and divide by the number of classes. Well, the numerator of that calculation is the range. It's the largest value minus the smallest value. So, can't get in, again, what we're learning here, very simple, right? Hopefully you'll remember this one, right? If somebody's asking what the range is, largest minus smallest value in the data set. Easy. Now, the problem with the range, as far as measuring variability, it doesn't really measure anything in the middle, any variability that's between those two values. So although it's useful to know the range, it's not a great measure for variability. The statisticians started thinking about what would be a better measure of variability that would include all the values in your data set. And what they did, they came up with this idea of deviation from the mean. Now, what is a deviation from the mean? Well, first of all, we would have to calculate the mean first. Let's say we have a sample of data, and we would calculate X bar, or the mean, first. And then what we would do is we would subtract the mean from each value in the data set. All right, so in this, these symbols in this box here, X1 represents the first number in the data set, X2 represents the second number, all the way up to Xn, n representing that last value in your data set. And so after we've calculated our mean, we subtract the mean from each of these values, and we get these n deviations from the sample mean. There's n of them. So if there's, n is 100, we would have 100 of these deviations. Now, you might think, hey, that's not a bad idea. We're using all the data in the data set, and we are sort of measuring how variable the data is. The problem with this is that if we wanted to come up with a summary measure of variability, that means we wanted to add up all these deviations. The problem is when we add up all the deviations from the mean in the data set, it always comes out to 0. Always. So if we added up all these deviations for every value in the data set, it always comes out to 0. So that's not very useful. That's not going to be a useful measure of variability, because obviously we want our variability to start at 0. Can somebody tell me what would be 0 variability in a data set? Can you explain in words what that would be? Anybody know? 0 variability. What does that mean?
Would that mean that all the data points are the same?
That's right. And wouldn't it make sense? There's no variability then, right? So whatever measure of variability that we use, the smallest value that we can have is 0. It can never be a negative number. It always has to be at 0 or positive. So 0 is the smallest measure of variability. Now, the sum of the deviations from the mean is 0, but unfortunately, that's not very helpful because it's always going to be 0, no matter how much variation there is. So if the numbers in the data set are different from each other, then the variability should be greater than 0. And the more different they are, the greater that number should be. I think it makes sense, right? Logically, you would expect a measure of variability to get larger and larger the more variable the numbers are, the more different the numbers are from each other. All right. So deviations from the mean, not great because of that factor of they add up to 0. So Well, somebody came along, a very smart person, and said, hey, wait a minute. The reason why the sum of the deviations from the mean comes out always to 0 is because the positive deviations, that is, when the number is bigger than the mean, are added to numbers that are smaller than the mean. In other words, when the deviation is negative, the positives tend to cancel out the negatives. And that's why we end up with 0. And somebody came along and said, why don't we just square the deviations from the mean? Whenever we square a number, if it's negative, it turns positive, doesn't it? So somebody said, all right, why don't we do that? We will take the deviation from the mean and then square it. And then we're going to add up all those squared deviations. And that will be always going to be a positive number or 0 if all the numbers are the same. And that meets our criteria for what a measure of variability should be. So statisticians came up with a formula, and they call it the sample variance. The numerator of the sample variance, it has this, again, this large Greek symbol, sigma, which is it's a large sigma. And then in parentheses, it has the deviation from the mean, x minus x bar, and it's squared. So we're adding up the squared deviations from the mean, adding them all up. Now, you would think you would divide by the number of numbers in the data set. You're averaging them. But in this case, because of some statistical reasoning, which is beyond this course, we're not going to get into it, the statisticians said, let's divide by the sample size minus 1. 1 less than the number of numbers in your data set. And they call this whole thing the sample variance, and they use the symbol s squared. S meaning, well, you'll see why they use s in a minute, but it's s squared. All right, small s squared. And that's called the sample variance. Now, looks good, right? It meets the criteria. If all the x's are the same, that means the mean is going to be the same as each of the x's, and that means our sample variance is going to be 0. And because we're squaring all these deviations from the mean and adding them up, if the values in the data set are all different, we're going to end up with a positive variance, sample variance, and it will be bigger when the numbers are different, or even more different than they could be. So this meets the criteria of what we're looking for. Can somebody here, maybe you could tell what is the issue with the sample variance? There's one problem with it, and it has nothing to do with the calculation itself, but there is something about squaring that is an issue. Can anybody think of it? Let's wait about 30 seconds here, since maybe somebody who's very clever could come up with an explanation. No? All right. Now, in whatever we are doing here, we're calculating things that we're measuring, right? The x happens to be a quantitative variable, all right? And we're measuring something. Now, would you agree that whatever we're measuring has units of measurement? So if we're measuring a person's height, we could be measuring their height in inches or feet or centimeters, whatever. All right, so there are some units of measurement. What happens to those units of measurement when we square each value in the data set? Well, they become squared, don't they? So if x is measuring height, and suppose a person 6 feet tall, they're 72 inches, right? That's 72 inches tall. When we do this deviation from the mean, which should be in inches, but we square it, we end up with squared inches. Well, that's not a proper measurement of variability because it's in the wrong units. So what do you think, what do you need to do to get back to the original units of measurement? If you're squaring something, and what do you have to do? If you want to get back to inches, if we're in squared inches, well, it says it right here. if you look just below that formula, it says take the positive square root. Take the positive square root. And when we take the square root, positive square root of the sample variance, we end up with what's called the sample standard deviation. So we've gone ahead and we have created this variance, which meets our criteria. And then if we take the square root of the sample variance, we get the sample standard deviation. We call it S. Now you know why we use less, because it stands for standard deviation, word standard. And that is the measure, that is a true measure of variability for a sample. Because not only does it meet the criteria of variability, in other words, it'll be 0 when all the numbers are the same, and will be positive when the numbers are different, but it will also be in the correct units. It'll be in the original units of measurement. So that's why they go to all this trouble creating a standard deviation from the variance, is because you need to be in the right units of measurement. All right, so that is the sample standard deviation, and that is something we use all the time in statistics. So it is a very important thing that I just showed you. And calculating it, all right, here's an example of a spreadsheet where they have all the values on the left column. The middle values are the deviation from the mean, after they've calculated what the mean is, in the middle here. And then they squared those numbers, so they're all positive here, and then they add them all up. That's the numerator for the variance. And then you just divide by the number of numbers here, -1, and that gives you the sample variance. The last step is to take the square root of that to get the sample standard deviation. Now, let's just stop sharing here for a second. Go back to our calculator. And where are you, calculator? Nope, you're not here. So, give me a second here. There we go. Sometimes if you don't highlight it on Zoom, it doesn't show up when you try to share. So, fortunately, I think we have it now. So, share it. And there it is. All right. And let's go back to our data set. Remember, the data set was stat, and hit enter. Remember that data set that it's from problem 3.25 in chapter 3. Anyway, if we wanted to find, go to one variable statistics, we hit stat, scroll over to calc, hit enter. Our data is in L1, it's defaults to L1, so we just scroll down, just calculate, hit enter. And what we notice, of course, on line number 1 up here is your mean. That's your mean. And then if we go down to number 4 here, the S, that's your sample standard deviation. Now, right below there, it has another standard deviation. It has a Greek symbol, sigma. Now, I said sigma before, right? Up here, these symbols here are sigma, right? Which means add up or sum. Well, that's the capital sigma. This is the small letter sigma, all right? This one down here, right below the S. And that is the population standard deviation. Notice that both the sample standard deviation S and the population standard deviation sigma are both listed here. If you know you have a sample, you're going to use the first number. If you know you have a population, you're going to use the second number. Now the question is, why are the numbers different? And the reason for it is that for a population, for the population variance, we still take the mean and subtract it from each value in the data set and then square it and add them all up. That's your numerator of the population variance. The denominator, however, is the population size. We don't subtract 1. So for population variance, we don't subtract 1, which means that the denominator is slightly larger in the population variance formula than for the sample variance formula. And whenever if the numerator is the same and the denominator is bigger, that means your fraction is going to be smaller. So the population standard deviation is always a little bit smaller than the sample standard deviation. So you pick the one that is appropriate for the problem that you're doing. If the problem is a sample, it deals with a sample, we use the S. If the problem deals with a population, we use the sigma. Okay, but that's the standard deviation that's listed in your calculator. If for some reason somebody asks for the variance is the square of the sample standard deviation or the population standard deviation. So whatever number you're using there, you square it and you'll get your variance. Okay, so that is this is where you would find it. You don't have to use actually use the formula. You have to know what the formula is, but you don't need to use it. You can find the standard deviation in one variable statistics as long as you've entered the data in your data set. All right, any questions about that? All right, so you can see your calculator saves you a lot of effort, right? A lot of effort. So let's get back to where we were. I think, make sure this is where we were. I hope this is the right one. Let's check. Yep, this is where we were. All right. So that is the calculation. Here in this slide here, they're actually showing you how to do it manually with the formula. But again, I just showed you don't have to do that. And again, the symbol for the sample variance is S squared. And the symbol for the sample standard deviation is S. While for the population variance, the symbol is sigma squared. And the symbol for the population standard deviation is sigma. Okay? Very clear on that? So these symbols you have to be familiar with for the rest of the course. And again, here is a summary of all of that. All right, so it's a good slide to look at. All right, and now for, let's see, this is slide 19. All right, now, besides the variance and standard deviation, there's another measure of variability called the interquartile range. Now, let's go back to the calculator for a minute. Again, we'll go back to that example, and we're in one variable statistics. Now, if we scroll down where we are here, let's scroll down with our bottom arrow key, if I can find my cursor here. There we go. Notice that in the bottom of the one variable statistics, there are 5 numbers here, which we're going to talk about it in a minute. It's called the 5-number summary. So below N here, we have the minimum, we have Q1, the median, Q3, and the maximum. I think I had mentioned this to you last time. The minimum is the smallest number in your data set. Q1 is what's called the first quartile, or quartile number 1, first quartile. It's also called the 25th percentile. We'll talk about percentiles in a minute, but what that means is that 25% of the data is lower than that, that value. The median, we have 36. That's the Q2, by the way, it's Q2, means 50% of the data is less than that value. And Q3 is also called the 75th percentile, means 75% of the data is less than 41.65. And then, of course, we have our maximum number value of 64. So that's called the 5-number summary. Now, what is the interquartile range? It is the middle 50% of the data. And the reason I say middle 50% is if Q1 represents 25% of the data being below it, and Q3 is 75% of the data below it, that means between Q1 and Q3 is 50% of the data. It's the middle 50%. So when you subtract Q3 minus Q1, when you subtract those two numbers, that's the length or the distance between those two numbers, and that is called the interquartile range. Now remember, the range is going to be the maximum minus the minimum, 64 minus 25.7 in this case. The interquartile range is Q3 minus Q1. It's 41.65 minus 31.7. Now, why do we mention the interquartile range? Because it's in the middle, just like the median is in the middle, because the variability is in the middle, it's not affected by outliers. So typically, if you have data that is very skewed either to the left or to the right, the measure of the center should be the median, and the measure of variability should be the interquartile range. Now, nobody in real life, nobody really does that, to be honest with you. They don't really use those, but it should be that way because the mean and the standard deviation both are affected by outliers. Now, why is the standard deviation affected by outliers? Because when we take the deviation from the mean, and we have very large or very small numbers in a data set, when we square those deviations from the mean for those very large and small outliers, it causes the standard deviation to be much larger than it should be, all right? Or not should be, but it makes it much larger. So the standard deviation, the variance are obviously too, they're both affected by outliers, just like the mean is affected by outliers. The interquartile range is not, just like the median is not. Okay, so that's why people talk about the interquartile range. Okay, so that is that. It's very easy to calculate because one variable statistics gives you that Q3 and Q1, and you just subtract them and you get the interquartile range. Okay, so let's get back to this here, and let's see, what slide are we up to? Number 19, and there we go. So this slide here just tells you it's a measure of variability that's resistant to the effects of outliers. I just explained why, and what the what happens with Q3 and Q1 is that you're breaking your data set into 4 equal parts, because the data that's lower than the Q1 is the lower quartile of data. All right, it's the lower 25% of the data. Between Q1 and the median is another 25% of the data. Between the median and the upper quartile is another 25%. And then all the data that's larger than the upper quartile is the highest 25% of the data. Right? Now, you might say, oh, how do I remember that? Well, I'm going to show you in a minute a graph called the box plot, which you'll be able to look at and see it. You'll be able to see it visually. That's why they have box plots. All right, but anyway, this is an illustration. This is not a box plot. This is just what they call a smooth histogram with a curve. And they plotted the lower quartile, the median, and upper quartile. And basically in this diagram, the area above the line here, that underneath the curve, this area here, this is the lower 25%, this area is the next 25%, this is the next 25%, and this is the next 25%. So this is a convenient way of breaking up the data set into 4 equal pieces. All right. And by the way, Q1 can be also described as the median of the lower half of the data set. So if you ordered your data set from smallest to largest, and then you calculated your median of the whole data set, that would be, you would have your lower 50%, which is below the median, and the upper 50% would be above the median. If you took the median of the lower half of the data set, that would be Q1. If you took the median of the upper half of the data set, that would be Q3. That's another way of defining the Q1 and Q3. Any questions about that? And of course, they describe it right here. And they describe IQR. IQR is just the it's just the symbols for interquartile range. So if you see IQR, you know it means interquartile range. All right, upper quartile minus lower quartile. Okay, so that's it for interquartile range. And then finally, in this chapter here, they give an example data set. So here's a data set, 20 people. This has to do with improvement scores, whatever that has to do with. It doesn't really matter. And because there's 20 numbers in a data set, if you order it from smallest to largest, take the two middle values and average them, that's your median. And then you take your lower half of the data set, all the numbers that are less than 5150, and find the median of those numbers. You get your Q1 or lower quartile, and they do the same thing for the upper half of the data set. All right, and then IQR is just different between those two numbers. But again, if you entered your numbers into your calculator, you just go to one variable statistics and just look up these numbers, lower quartile and the upper quartile. The median, it's all there for you. Only for the IQR, you have to calculate that. The calculator doesn't give that to you. All right, so let's stop sharing this and we'll go to 4.3. So 4.3 is the box plot here. Now, we've just talked about the idea of splitting the data set into 4 equal pieces. And what we use for doing that is our 5-number summary. It's the smallest number, Q1, the median, Q3, and the largest number. That's the 5-number summary. And we plot it along the number line, and we draw a box around Q1 and Q3, and we create what's called the box plot. Now, there's a couple different types of box plots. One is called a skeletal box plot. And then there's one called modified. The modified one is the one that we'll be using in this course, but let's look at the skeletal one first. So how do you create one? Well, your calculator can do it. I'll show you in a minute that your calculator can create one, but basically you draw a number line which measures the variable that you're looking at. And then you plot your 5-number summary, and you create a rectangular box where the lower edge of the box or left edge of the box, depending on how you draw the box plot, is going to be the Q1, and the other edge is going to be Q3. And then the length between those two, the length of the box, is going to be your IQR, because it's the distance between those 2 points. All right. And then beyond the box, you're going to have your smallest values and largest values. But I'll show you what it looks like in a second. So again, going back to the other example, if you have all these numbers here, 5-number summary, and you plotted it, well, here's a summary of what those 5-number summaries, those 5 numbers are. Okay. Smallest value in that data is 1200. Large Q1 is 3550. The median is 5150. Q3 is 6150, and the largest number is 7700. And we would plot it like this. Now, sometimes box plots are plotted where it's plotted horizontally like this, and sometimes it's plotted vertically. All right. So in the previous slide, when they said to the left or lower, it would be to the left when you're plotting it. The Q1 would be to the left for the box, and you're plotting it horizontally, and it would be the lower part of the box when you're plotting it vertically. But basically, here's your box right here. The left end of the box is Q1. All right, if you just moved your finger down to the bottom here, it would be down here. It would be between 3,000 and 4,000, whatever that number is. The median is the vertical line that's inside the box. That's that you draw your median right there. And then whatever that number is, and then the right side of the box is going to be Q3. Now, what about these lines that extend out? These are called whiskers. So this is called the box, and these are called whiskers, left whisker, right whisker. Typically, sometimes people call the box plot a box and whisker plot, a whisker plot, but we're going to call it a box plot. The left end of this whisker on the left, the very end of it on the left is your minimum value, and the very right end of the box of the whisker on the right here is going to be your maximum value. So you have your minimum Q1, median, which is Q2, Q3, and maximum value, and that's your box plot. All right. Now let's just go to, well, actually, that's not good at calculator yet. I just wanted to show you. Now, one thing they're showing you here is that you can do comparative box plots. That is, you can, if you look at two populations, you're comparing the same data along the same scale, you can compare them and look at, the distribution of the numbers. And box plots, by the way, can tell, you can look at a box plot, you can tell whether we have a symmetrical or we have a skewed left or skewed right distribution. And the way to figure that out, the easiest way of figuring it out, let's go back to that box plot we just saw a minute ago, this one here. Remember that the median, 50% of the data is less than the median, 50% is greater than the median. So the median is that vertical line inside the box, and it looks like it's somewhere around 51 or 5200. And here is the maximum, it's about 7800. So the distance between the median and the maximum value is 50% of the data. The distance between the median and the smallest number is 50% of the data. So it looks like to me, from looking at this, that the 50% to the right, the data is more squished together because the distance is smaller, right? It's less than 3,000 from the median to the largest value. But from the median to the smallest value, it's almost 4,000. It's about 4,000. So it's a larger distance, which means the data is more spread out. So this looks like it's probably skewed to the left because the data is more spread out or tailing off to the left. So the only way to know this, of course, is to maybe do a histogram also with the box plot, and you'll be able to tell. But you can tell things like that using a box plot. And by having comparative box plots, you can compare things like the median, you can compare the relationship with lower quartiles and the upper quartiles and things like that. So sometimes people use box plots to compare, and that's what they mean by comparative box plots. Here's an example here. And you could tell by just looking at this, the two box plots, that the one on the top there, the one on the bottom is more variable than the one on the top, right? The distance, the range is much bigger on the second one that's called variable priority than the fixed priority one on the top. Okay, so you could, and the median is bigger on the variable priority one. It's a bigger median. You could tell the IQR is larger also. Things like that, just by staring at the two box plots. Now, a modified box plot is sometimes used, and a modified box plot is like a regular box plot, except we're able to, in addition to drawing it the way we've done, if there aren't any outliers, we want to represent them by circles, either filled in or open. All right, now here is how you determine an outlier right here, this formula here. And by the way, we're going to stop at 4.3 today, running out of time. So what we're going to do on Monday, besides talk about regression, is we're also going to do 4.4. So I'm going to finish 4.4 on Monday, along with the couple chapters 5 and also scatter plots in chapter 3. All of that will be completed on Monday. All right, so we'll catch up on Monday. But what I'm going to do now is talk about this modified box plot, and then I'll show you how to do it with your calculator. All right, and that'll be it for today. So your homework, by the way, will not include anything from 4.4 yet, the first homework assignment, but anything that I covered today through today is a possibility for homework, for the first homework assignment. All right, so let's take a look at a modified box plot. And the best way of doing it is to actually show you an example. Here's an example. Here's the data set 20 things that we're measuring. Looks like some sort of width or length. Again, it doesn't matter what we're looking at. It's just 20 numbers here. All right. And if we enter all those numbers into our calculator and we go to one variable statistics, we end up with our 5-number summary. We have our lower quartile, median, upper quartile. We can calculate IQR. Now, once we've calculated IQR, what we do is to determine any outliers, we do 2 calculations. The first one is we're going to take our IQR and multiply it by 1.5. That's what we're doing here. We're taking the 0.075, which is our IQR, and multiplying by 1.5, and we get a 0.1125. We also multiply the IQR by 3, and we get 0.225. And it's just double of this 0.1125. All right. Now, what do we do next? Well, to determine outliers, let's just look at the 1.5 IQR number first. Let's say we want to determine what are called just moderate outliers, all right, regular outliers. So one thing we can do is we can take our upper quartile number, which is 0.681, and add to it the 1.5 IQR number, which is 0.1125, and we get this number 0.7935. We take our lower quartile and subtract the 1.5 IQR. So we're going to take our 0.606 and subtract 0.1125, and we get this number. Now, here's the deal. If any numbers in your data set are larger than 0.7935 or smaller than 0.4935, they are outliers. All right? And that's a definition of an outlier. So those are outliers, period. Okay? Now, what if we want to determine if a number in your data set is an extreme outlier? Well, what we're going to do is, let me see if they have it here. Yeah. What we're going to do is we're going to, instead of adding 1.5 IQR to your upper quartile, we're going to add 3 times IQR to your upper quartile. And we'll do the same with the lower quartile. We're going to subtract 3 IQR. If any numbers in your data set are bigger than 0.906, it's an extreme outlier. Not only is it an outlier, it's extreme outlier. And then when we subtract 3 IQR from the lower quartile, any numbers that are smaller than that is also an extreme outlier. All right? So that's what the book is going through here, the difference between a regular outlier, a mild outlier, they're calling it here, and an extreme outlier. All right? And as far as plotting them is concerned, if a value in your data set is a mild outlier, that means it's not extreme, but it's an outlier, then we plot it with a dot that's filled in. If it's an extreme outlier, we plot it with a dot that's not filled in. Okay? And then the whisker stops at the number that is the next smallest number from the outliers that we plotted. So whatever the next smallest number is from this mild outlier here, that's the ending point of the whisker on the right here. Now notice on the left here, there are no outliers. Nothing is being plotted, so the whisker goes all the way out to the minimum value. Here, these two numbers, these two large numbers in your data set are both outliers. One is mild, one is extreme. So read through that. I think you just need to do a couple of examples and you'll be okay. Let me just show you in the your calculator, if you don't mind. I'll just go about a minute past today. If you wanted to create let's say you've already set up your calculator with the window that you would have done for doing a histogram. The only thing you have to do for the box plot is go to, again, second y is equal to, which is your stat plot, hit enter, and then you scroll down. And what you can do now, what's very interesting here is that now this is for the 84 calculator. I'm not sure if the 83 calculator has this, but if you scroll over, you have two box plot options here. All right, you have this box plot here. You have to hit enter to highlight it. All right, or you have this one over here. So the one in this calculator, the first one is your modified box plot, and the second one's going to be a skeletal box plot without the outliers. So this may be useful to you to have the ability to take a quick look at it. So I'm going to highlight it like I did, and I'm going to hit the graph here, graph button, and it looks like I am stuck. This sometimes happens with this online 84 calculator. But anyway, you can see in the screen here, I did this earlier. Here's your box plot, and actually, if you use your trace button, you can actually trace the minimum Q1, the median Q3. You could trace this value here, and then there's a couple values at the end here, which are outliers. Now, I don't think the calculator distinguishes between mild and extreme outliers. It just determines an outlier, and it uses the formula with 1.5 IQR. So that's the only formula that it uses when it determines an outlier. Okay, so it doesn't look at the extreme outliers at all. And then if you look at the calculator, the one that's over here, that's the skeletal box plot without the outliers. All right. So, and actually, I was showing you something without you didn't tell me, but you didn't see that, did you? Nobody said anything. I wasn't sharing the screen with you, I don't think. Let me just share the screen with you. This is what I was talking about. So again, when you get to stat plot, you just scroll over, and the very first, at least with the 84 calculator, the first one that you see over here is your skeletal, your modified box plot, and then there's a skeletal one next to it. And down here, I did a skeletal box plot earlier, and what I was saying is these ones to the right here are outliers, but I don't think this calculator distinguishes between modified and extreme, so it just looks at uses the 1.5 IQR formula for determining outliers. All right, so that's it for section 4.3. Any questions? I hope you're all paying attention. Looks like some of you have your videos off. Please pay attention during this here, because this is how you learn. It's not a good idea to be looking at your phone or anything else while you're taking this class. So that's why I like to have the videos on, so you're sort of paying attention. All right, so once again, as I said, I'll say it again for the recording. Everything through section 4.3 will be chapter 3, chapter 4 through 4.3 will be subject to homework. I'll post the first homework tomorrow, late afternoon probably, and I'll give you a due date. We'll give you a few days to get that done. And then 4.4 and anything I cover on Monday will be the second homework assignment. Okay, and that'll come also next week. Any questions? No questions? All right, so that's it for today, and I will see you guys on next Monday. And again, look out for my email about the homework.